Okay, so section 13.2 is about the acidity of alcohols and phenols. This is a big deal. I would have a difficult time if I were going to try to exaggerate how important this is. So give it your attention and you'll be glad later. So I'll remind you what an acid-base reaction is. We did this, I think, in chapter 3, but it's very important here. What you have is, in an alcohol, you've got a hydrogen, which is bonded to an electronegative element, namely oxygen here, right? And you have a base that comes in, and you can see the reaction here, right? I'm just going to redraw it. Base comes here, the electrons go off onto the oxygen, and those electrons are here, right? These electrons are here. I'm going to call those electrons 1. These are electrons 1. Agreed? Okay. And so you can see what happens. A molecule of hydrogen gas is made, and that bubbles off as gas. So this is, you can see why this is a nice way to make the conjugate base of an alcohol, which we call an alkoxide. I don't think it's written here, but yeah, here it is. Which we call an alkoxide. Okay? So an alcohol makes an alkoxide if you deprotonate it. Very important reaction. And we're going to learn a lot about, we're going to use it a lot, and we're going to use it to make things, and we're also going to use it to understand things. So big deal. This is a big reaction right here. Now, another possibility is to take an alcohol and add sodium, potassium, or lithium metal to it, right? And this will strip off a hydrogen and make the alkoxide. Okay? H2 gas, which bubbles off, right? That bubbles off. By the way, this is on page 583. So please consider looking at that. All right, so here's two ways to make alkoxides. The first is with sodium hydride, which is a strong base. Strong base. Real strong base, right? It's got to be stronger than that base. Okay, because this is really an equilibrium reaction. Okay. And so it's real strong, but it's not really a good equilibrium reaction, though, because we're losing one of ours. So Le Chatelier's principle just pulls it off all that way, right? And then the other way is to add sodium, potassium, or lithium metal. This will give us two alkoxides. Now, that's how we make alkoxides. Let's talk about how we can evaluate the strength of these bases, or the strength of the bases if it's an alkoxide, or the strength of the acid if it's an alcohol. So first of all, recall from chapter 3. Where's my pen? I can't find it. There you go. Okay, recall that we use this acronym REO to qualitatively assess the strength of an acid. So first of all, we consider the atom that the hydrogen is bonded to, right? And so if we're talking about R as an alkyl group, that's going to be a carbon, right? And so that bond is a very strong bond. So it's going to have a very high pKa, a very bad acid, right? Increasing acidity, so very low acidity, okay? A pKa of 45 to 50, we're going to use these a lot, and that'll tell us low acidity, all right? Now, if the hydrogen is bonded to a nitrogen, it's much better. That doesn't look a lot better, but it's 10,000 to 100,000 to a million times better of an acid, okay? Still not a very good acid, right? Because you know these are actually such not good acids, we call them bases, right? Okay, now if the hydrogen is bonded to an oxygen, can you see what we're doing here? Carbon, hydrogen, nitrogen, hydrogen, oxygen, hydrogen. If it's bonded to oxygen here, then its pKa is between 15 and 18, or maybe 14 and 18, right? So you still have the carbon here, but watch out. See, that carbon is bonded directly to the hydrogen. The hydrogen's here bonded to the oxygen, okay? So here, X is typically used for a halogen. Let's talk about that. That's going to have a pKa of, oh, I don't know, -7, something like that. Okay? Another X would be fluorine, which is closer to 3, a pKa of closer to 3, right? So these are very good acids. Good acids, all right? So what we've just done here is we've considered the atom that the hydrogen is bonded to. All right, now what does the R stand for? R stands for resonance. So let's consider resonance factors. So you can see that this hydrogen is bonded to an oxygen in both cases, right? So the atom is no different. But, and then actually the next atom over is a carbon, right? So that atom's no different. Okay? But let's consider the resonance possibilities that exist. So if we abstract the proton off of this guy, and we abstract the proton off of this guy, we're going to be left with phenoxide. Can you read my writing? And over here, we're left with, our marker's crooked, isn't it? We'll be left with cyclohexanoxide, right? Cyclohexoxide, all right? We don't call it very often, all right? So, but either way, you can see a base here. Can you see a base? And a base? Well, which is more stable? Right? The more stable base, of course, is going to make the stronger acid. So here's how we know it's more stable. If we have resonance structures. This one we're evaluating resonance. So do you have any resonance structures here? Can that go here? No, it cannot, because that carbon is already satisfied, right? It's already got its octet satisfied. This one, that one can go here, because if it does, these electrons can go here. And that will give a resonance hybrid which looks like that. Can you read my writing? Okay, if you can't, you got to ask yourself what's going on here with these. Really, you need to follow this out. So what I'm asking you to do here now is to pause the video and show all possible resonance contributors. This is a big deal. It's a very valuable exercise. Do not skip it. Very valuable exercise. Okay, so we've considered, let's see, if we're doing ARIO, we've considered the atom, we've considered resonance. Now let's consider induction. You know what? I want you to look at this. I don't want to do this question with you. We're gonna go on to induction. But look at this. Given the relatively low pKa of phenols, will sodium hydroxide be strong enough base to deprotonate a phenol? Okay. You know what? I really do want to do this. I'm gonna do this. Here's what we've got. So, what you've got. There's hydroxide, right? There's phenoxide. What's the other product here? It's water, right? Can you see that? Okay. Now, if that's the case, we see that the pKa of phenol is 10. I'm going to put it in a box, okay? And the pKa of water is 16, right? Can you see it here? pKa of water 16. So tell me, which side of this reaction does the equilibrium predominate? Which is it? Well, the stronger acid is here. That's the stronger acid, right? So it's going to go that way. Okay? Stronger acid wins. The stronger one gets to act like an acid. So it goes that way. So the question is, given the relatively low pKa of phenols, will sodium hydroxide be a strong enough base to deprotonate a phenol? And the answer is, aha, yes. Okay? My family's coming in here, so we're going to get a little bit of background noise. Go tell them I'm recording. Thank you. So, all right. Now, what's the next one? We were doing ARIO, right? Go ahead and tell them, honey. Go ahead and tell them. ARIO. Induction is the next one. Right? So that is the drawing off of electrons through bonds, right? Or through hyperconjugation. So induction, unless there's an electronegative group nearby, induction will not be very significant. Okay, but here's what we got. Carbon here, and a carbon here, and a carbon here, right? Oh, that's messy, very messy. 2 hydrogens, 3 hydrogens, 2 hydrogens, right? So let's consider what let's consider this. What's going on here? Do you see electronegative groups here? Okay. So electronegative groups are electron withdrawing, right? Look at that. Electron withdrawing. And so they're drawing the electron, they're drawing this negative charge that way. Do you see it? How big a deal is it? Well, we look at the pKa's. Wow. Big deal. Look at that. It's off by an order of over 1,000, right? So trichloroethanol is over 1,000 times stronger of an acid than ethanol. So induction is a big deal if there's an electronegative group nearby. Okay? And in this case, if you've got 3 electronegative groups, and they're as electronegative as chlorine is, then you get an increase by over 3 orders of magnitude, an increase in acidity. Okay? So we've taken care of atoms, we've taken care of resonance, now we've talked about induction. Now we talk about orbitals. In what type of orbital do the alkoxide electrons reside, and how does that affect their stability? Do I have a slide for this? No, I don't. Okay, so I need to draw one here. What we have, let's talk about this. Okay, so the pKa of this hydrogen is about 45. The pKa of this hydrogen is less, maybe 40. The pKa of this hydrogen is 25. What? What? Are you serious? The pKa of that hydrogen is 25? Why? Here's the answer. Okay, so that's review from chapter 3, but that's something that you want to go back and look at. The orbital the electrons that are left behind resides in. Okay, bring that question to class if you like. Okay, so the last point here is solvation is also an important factor that affects acidity. Water is generally used as a solvent when measuring pKa values. Which of the acids below, or the alcohols below, is a stronger acid? Well, we see ethanol is a stronger acid, right? You can see that. And why is it? Well, I think I've got a picture here. It's because when ethanol loses its proton, it becomes ethoxide, right? And so ethoxide, you've got an electron density map here. Can you see the solvent, which is water molecules, is going to try to take that negative charge, which is red, and try to mollify it, right? Try to make it feel like it's not so angry. So it turns out there's more room around this ethoxide negative charge than there is around the tert butoxide negative charge. So it's harder to get. It's harder to get this negative charge satisfied by solvent molecules. Okay, so solvation affects the difference in acidity between ethanol, which looks like this, and tert butanol, which looks like this, right? So this is a better acid. We saw on the previous page. This is a better acid because the conjugate base is more stabilized. I'm going to write that out. This is a really big deal. Conjugate base